Hi boys and girls, this is lecture 7.9, the topic, volume, the disk method, part 2. In the last lecture, we discovered that we can find the volume of a solid having a circular cross-section whose area is A equals pi r squared. This means that taking any curve and revolving it around an axis generates a three-dimensional solid. In order to discover the volume of that solid, we take a cross-section, which is a circle since we rotated the curve around an axis, and add up an infinite number of areas of circles, which becomes equivalent to the volume of the solid. Well, the idea of using the integral to add up an infinite number of things doesn't just work with circles. It would work with squares or rectangles or triangles or any known cross-section. So now we're going to use the integral to add up an infinite number of areas of shapes other than circles in order to find the volume of a three-dimensional solid. The method that we used before can be generalized to solids of any shape, as long as you know a formula for the area of an arbitrary cross-section. Some common cross-sections are squares, rectangles, triangles, semicircles, and trapezoids. Notice in this figure that the base of this solid is a parabola. Previously, we were taking a curve and rotating it around an axis to generate a solid. But now we're going to let this region be the base of the solid, and we're going to build a three-dimensional shape on top of that region. In this case, the cross-section is going to be squares. So notice that the width of the square is the distance from the x-axis to the curve. And of course, since a square is side squared, that means that's the height of the square as well. So the equation of the function curve squared will represent the area of the square. So from this point on the x-axis to this point on the x-axis, we'll use the integral to add up an infinite number of areas of squares, and that sum will be equivalent to the volume of this three-dimensional solid. It's also possible to build a solid with cross-sections that are perpendicular to the y-axis. Here we have the same parabolic region as the base of the solid, but in this case we're using cross-sections that are perpendicular to the y-axis. Notice in this case the width of the square is the difference between the left side of the parabola and the right side of the parabola, and we would integrate from this point on the y-axis to this point on the y-axis, using the integral to add up an infinite number of areas of squares along this section of the y-axis would give us the volume of this solid. So for cross-sections of area taken perpendicular to the x-axis, your functions will need to be in terms of x, and you'll be integrating from a point A to B on the x-axis. But for cross-sections of area taken perpendicular to the y-axis, your functions will need to be in terms of y, and you'll be integrating from a point C to D on the y-axis. Find the volume of the solid shown in the figure. The base of the solid is the region bounded by the lines f of x equals 1 minus x over 2, g of x equals negative 1 plus x over 2, and x equals 0, which is the y-axis. The cross-sections perpendicular to the x-axis are equilateral triangles. Notice that our cross-sections are perpendicular to the x-axis. That tells us how we need to set up our integral, and we're also told that they are equilateral triangles. The cross-section will determine the shape of the three-dimensional figure. If we have equilateral triangles, we get the shape that you see here. However, if this cross-section were squares, or rectangles, or semicircles, it will build a different three-dimensional shape. So now that we know what the cross-section is, equilateral triangles, we need to know the area of that cross-section. The area of an equilateral triangle is square root of 3 over 4 times s squared, where s is actually the length of one of the sides. So let's determine the length of one of the sides of the equilateral triangle using f of x and g of x. The length of a side is the difference between f of x and g of x. So that means f of x minus g of x, which is 1 minus x over 2 minus negative 1 plus x over 2. When I distribute this negative, this gives me 1 minus x over 2 plus 1 minus x over 2. In simplified form, this is 2 minus x. So this is the length of one side of the equilateral triangle. Therefore, the area of our triangular cross-section will be square root of 3 over 4 times the length of our side squared. Now it's time to set up the integral. We're going to integrate an infinite number of these triangular cross-sections from 0 to 2 on the x-axis. I'm also going to place the constant square root of 3 over 4 on the outside of the integral. That means I have inside 2 minus x quantity squared dx. Of course, this is a composite function, meaning that this is the u part of my integrand. Du is negative 1 dx, so I need to place a negative in the integral and compensate by placing a negative on the outside of the integral with the constant that is already there. Now I'll use the power rule, adding 1 to the existing exponent and then dividing by that new exponent. So I'll have negative square root of 3 over 4 times 1/3 and then 2 minus x quantity cubed from 0 to 2. Multiplying these two constants together gives me negative square root of 3 over 12. And now I'm going to put 2 in for x and get 2 minus 2, which is 0 cubed, 0 for the first term. And then when I put 0 in for x, I get 2 cubed, which is 8. When I multiply negative 8 times negative square root of 3 over 12, my result is 2 square root of 3 over 3 cubic units. Remember, this is a volume. And that's your answer. In our last example, we're going to find the volume of the solid whose base is bounded by the graphs of y equals x plus 1 and y equals x squared minus 1 with the indicated cross-sections taken perpendicular to the x-axis. So for both solids, the base is going to be this region. But for letter A, we're going to use cross-sections which are squares perpendicular to the x-axis. And for letter B, we're going to use cross-sections which are rectangles with a height of 1 perpendicular to the x-axis. Since the area of a square is side squared, we need to determine the length of a side of our representative cross-section. And of course, the length of the side of this square is the difference between the two function curves. To help us visualize this, let's take a look at this pseudo three-dimensional graphic. You can see that I've constructed squares perpendicular to the x-axis at intervals between these two curves. And for each square, the length of the side is the difference between the two curves. That varies, of course, as we move along the x-axis, depending on how the curves are interacting with each other. The expression that we construct for the length of the side of the square will take into account those variations as we integrate from negative 1 to 2 on the x-axis. So the side of the square is going to be the line minus the parabola. So x plus 1 minus x squared minus 1. When we simplify this expression, we're going to have negative x squared plus x plus 2. And since the area of a square is side squared, we'll integrate from negative 1 to 2 our expression negative x squared plus x plus 2 squared dx, and this integral will calculate the volume of that solid. To integrate this, you would need to multiply this trinomial times itself, integrate all of the individual terms, of course plug in 2 and negative 1, and you would end up with a volume of 81 over 10 cubic units. Now let's set up the integral for letter B. The area of a rectangle is length times width, or base times height. You can see in our cross-section that the length of the base of this rectangle is once again the difference between the two function curves, and that is this expression, negative x squared plus x plus 2. The height is specified to be 1, so the area of this representative rectangle will be negative x squared plus x plus 2 times 1, which of course is just negative x squared plus x plus 2. So to integrate, once again, from negative 1 to 2, we would have the expression for the area, negative x squared plus x plus 2 dx. And when we integrate, we'll end up with negative 1/3 x cubed plus 1/2 x squared plus 2x. And when you plug in 2 and negative 1, your endpoints of integration, you'll find that the volume of that three-dimensional solid is 9/2 cubic units. That's it for today, and that concludes the Unit 7 lectures. I leave you with this quote by Martin Gardner. All mathematicians share a sense of amazement over the infinite depth and the mysterious beauty and usefulness of mathematics. As you've studied calculus this year, I pray that you've experienced this very sentiment many times over. God bless you, boys and girls.